Hello, welcome to our Breadboard computer project,
I'm Dylan.
and I'm Rithvik. So our project objective was to build a 8-bit computer from scratch, without any prior knowledge of how the computer works. So throughout this process, we were able to learn the different parts of a computer and teach other people to build it as well. And we also made documentation on a website to help people kind of replicate the steps of each component and help them build it as well.
So just some terminology before we get started that we're going to use. So binary is basically a number system that uses zeros and ones, and just a video, just that's what turning on and off is binary. Also logic gates, they're basically a device that or chips that perform a true or false operation based on binary inputs, and then they will have a binary output.
And we also use a oscilloscope, which is a voltage measuring device that just displays the waveform of a voltage signal on the screen. As you can see on the device here, it shows the peak to peak voltage signal.
So this is So this is the architecture of our computer. So this it starts at the clock, which is basically like the backbone of our computer that synchronizes all the components. The memory address register has an address input that gets information from the RAM, which is where the data and info storage is held. And then the instruction register gets the instruction from the RAM to give to the control logic, which basically sends it out. And the program counter is keeping track of that instruction, while both of the registers have temporary data storage in them, which then can be calculated by the ALU and is outputted through the output register and then displayed. And all this information runs through an 8-bit bus.
So we have different components that make up this. There's a clock, which is part of the CPU. We have the program counter. We have a memory address register, the RAM, which is random access memory. We have instruction register, control logic, which is a very important part of the CPU and of the computer in general. The two A and B registers, the arithmetic logical unit, which performs arithmetic operations like addition, subtraction, whatnot. We have the output register, and we have the bus that kind of connects each component and transfers data, and it's just like connects every single component together. So moving on to CPU, this is a very important part of the computer. It's called the central processing unit because it performs all the instructions needed to keep the computer running. It does the fetch, decode, execute cycle. As you can see here in the diagram, there's three components. We have a clock, and basically what happens is that with each tick of the clock, we go through one step of the fetch, decode, execute cycle. So overall, it just goes through all the instructions processed in the RAM, and it just like goes and processes each of them until all the instructions are done. And while it does this, it sends control signals to the ALU. So the ALU will determine what operations it needs to do. And here's just a diagram of everything.
So this is a software we had. We use an EEPROM, which is basically a memory chip that's used for storing programs and data based on the computer's instructions. So to simplify the process of writing data to the EEPROM, we used Arduino. So we were able to code it to have an easier way to actually write data into the chip. And this can be used simple like a blinking, turning on like a blinking LED, but also for something more complicated like controlling like a microcontroller. So, like we were saying before, the clock module. So this basically keeps the signal moving in the control unit, and this uses three logic rates: a NOT gate, a NAND gate, and an AND gate. NOT and NAND gate convert inputs inverse the clock signal and controls the clock signal, while the AND gate combines both single signals for an output. And the clock module was used a lot for testing for like the RAM, the ALU, and the program counter. And we also used oscilloscope to test the actual output of the clock module.
So next we have the A register, which is also called the accumulator. And what it does is basically it does like arithmetic operations, and it stores the result of these operations. For this module, we use a transceiver chip that kind of like receives and like sends data. And we used LEDs to test and debug whether the actual component is working. And yeah, it just shows out the output of algebraic operations, telling us that we can do it. Yeah. And the B register is kind of similar, except it's used for temporary storage of data and holds data during transfer. For the B register, we use two 4-bit registers, which each of them store 4 bits of data, which is 8 bits total because it's an 8-bit computer. And we also use a bidirectional bus transfer, which just is data flow between A and B registers. Here's a diagram of the B register and old components.
So then this is the ALU, which is the connection between the A and B registers. It basically outputs the sum and difference of the registers. So if there's 5 in the B register and 3 in the A register, and you want to subtract that, the difference of 2 will be shown through the ALU. And this uses an exclusive OR gate, which helps determine the sum, and also uses a 4-bit binary adder. So, which you see right here. Then we also have a RAM that uses, which is the random access memory that uses 4-bit addresses, meaning 16 bytes of RAM. And this uses flip-flop for the data storage and also uses a multiplexer, which means that when it has multiple inputs into the chip, the multiplexer will allow it to be only come out as one single line of output. And it also has a buffer, which is a bus transceiver chip, which basically allows different directions of data to flow in to both buses. And finally, we also have a program counter. And basically, this counts in binaries based on the computer's execution. So this uses a JK flip-flop chip, and it's basically used to store the binary elements. And this we connected to the clock module, as you can see here, to test the input. So the green and orange lights were basically based on the clock signal.
So next up, we have our challenges. So obviously, we're kind of new to this. We've been doing a lot of computer science, so it's definitely a steep learning curve, kind of like researching and learning more about CPU and its functionalities. But it was definitely rewarding at the end as we understood the architecture and we got familiar with components and reading data sheets, whatnot. So yeah, it was really nice experience. And another challenge was that there was a lot of wiring issues that needed significant amount of time troubleshooting, debugging. Like there's a few examples, like there was power supply backwards, there wasn't strips weren't getting power. And this was definitely like true with clock and especially with more complex circuits like the ALU and A and B registers that just used a lot of wires in general. And to kind of debug this, since it took a lot of time, we used an oscilloscope to check the voltages and signals just to make sure all the components were working and that we didn't have a false sense of like, oh, this was working when in actuality it was not. Yeah, so our results was that we made the clock module, which is like the backbone of our computer to test all of our features. We have the different functionalities here. We also build the ALU, which connects the A and B register and performs different arithmetic operations. And we have the RAM, which is really important for storing data and storing instructions for the computer to execute. And finally, we have the A and B registers that just connect to each other and let the ALU perform operations.
And this is what we have all together, which it's not a full working 8-bit computer, but everything that we had the program counter, the RAM, and the clock module all connected together, and you can see how all these LEs are working together.
So in conclusion, we learned to understand the CPU architecture, and we were able to learn and teach other people to build these components by themselves. We also created an instruction guide and documentation. There's QR code at the end that leads you to the website where you can kind of follow these instructions and build your own computer.
In the future, if we did have more time, obviously we would try to finish the whole computer, but we would also try to expand the breadboard computer to be able to run actual like programs in assembly code via an online IDE. And we'd also add more peripherals like displays and keyboards because our current one doesn't really have a lot of those. We'd like to thank Professor Richard Martin and Professor Richard Howard, which are our advisors, and Jenny.
We also like to thank Jenny, Ivan, and all the WinLab staff for this awesome opportunity. We definitely learned a lot, and it was really valuable. So thank you.
So the clock was running at like 3 seconds per per tick, but we could control that using different resistors. So we used a 100K ohm resistor right now, but if we want it to be higher or lower, we would just switch the resistor out.
Yeah, we use the same clock for.
So like the CP, like the one we built currently was like the control logic that we built was based on like all the like materials we were given. So because it was only like an 8-bit computer, it wasn't very strong, but we hope to have something that could actually run calculations like addition and subtraction, and even maybe like something like multiplication. But that was basically like the function of the whole CPU.
Yeah, I think definitely if we had more time, it would be a future goal. Sure. We got it from Ben Ear. He has a YouTube channel just like going through how to build.